Hello everyone, welcome back to my channel. So today I'm gonna do a problem number of connected component in an undirected graph. So you have a graph of n node. You given an integer n and an array a indicates that there's an edge between node A1 and B, node A and node B in the graph. Return a number of connected graph. So in here, as you can see, example one, this connected graph is one component. This is the second one component. For the example two, the whole thing is one component. So the output is returned one. To make it quick, the whenever you look at a graph problem, you must think about BFS or DFS. For BFS, for this specific problem, let's think about BFS first. You go through every node, you check that this node is not connected to anything, so you make a count +1, something like that. And then you go to the next node. Oh, this one is, you go to the next node, let's say one in here, but you already visited, so you don't do it anymore. Or maybe you go to two right here, everything is visited, so you don't check it anymore. Yeah, you go to three and four, you start doing three right here, and then you see this one have not visited. So you take this one, and then whenever you finish, you count as a whole again. So the count +1 again, so now it's two. So that is a BFS approach. But today we're gonna do something a little bit different. This problem is also introduce us about unifying. So let's say arbitrarily we have all the nodes. All the node is not connected to anything. Like we do not know. We only have an integer n right here. We do not know it's connected to what, right? Let's say right here. So in unifying, let's say we have an owner node is, first of all, owner node is connected to itself. So owner node is the parent of itself, right? Really cool. So let's say in the age node we have 0 and 1. So in here we're gonna say if it's 0 and 1, we're gonna union 0 and 1. So these two nodes, since it's the parent of itself, and both of them have the same height, so right when we union them, arbitrarily pick between 1 and 0 and 1, right? So we're gonna do something like this. Let's choose 0. Oh, let's not do that. Let's do it like this. And 0 is still the parent of itself, right? Oh man, let's remove this. So in here we can say that 0 is the parent of 1, and 0 is the parent of itself. Let's try to do this a little bit better. Let's remove all of this, connect those two. So now we move on to the next one. We have 1 and 2, right? So for 2 and 1 right here, we have to union it, right? So when we try to union these two, we check that what is the parent of them. So the parent of 1 is 0, the parent of 2 is itself, right? So when we union that, we also rank it, right? So when we rank it, we see that this one is higher than this one, so it's a little bit better to take. So when we union 0, these two elements together, right, these two things together, we're gonna do, what if we take 0, this one, and then we plug it into, it's gonna create a linked list like this. So it's not really efficient when we traverse to find the parent, grandparent, the root of that component, let's say. So the best way to do it is to take this node and then make it a child of this component. So we're gonna do it like this. So in here, as you look, this tree, like this graph, is look more balanced. Same thing with the 3 and 4. We have a 3 and 4 right here. So the 2 is 2. So this 2 is since they are together, we just arbitrarily plug them in, right? So arbitrarily plug them in here. Yep. So right now we have 2 components, but the question is how we're gonna keep track of it, right? So the way we're gonna keep track of it is, in the beginning, since we have all the islands right here, I'm just gonna say it islands, right? We have 5 different islands. Just arbitrarily think about n is 5, right? So it means that we have 5 components. But each time we union it, we decrement it by 1, right? So we union it 3 times. So the moment we union it, we lost 1 component, right? So whenever we union the 2 component, we decrement it by 1. So at the end, as you see, I union it by 3 times. So right now n is only 2, and 2 is our answer. So that is basically how union find work in this problem. I think that's all it is. Let's try to code it up. So first of all, let's start with a main function right here. So my main function just call union find like this, pass the n in, and then for node 2 in the age, right, we're gonna do a union, something like this, and then we return the union. Well, I did it really wrong, so let's do this. Oops, what am I doing? Like that. And then on the top of the page, I have a class name called union. So this is where I'm gonna do my union find stuff, all the good stuff. Let's start with this. Oh, damn it. What the fuck? Let's start with put this. So in it, right? And then self. I'm gonna take the n right here. And with that n, we have the parent node, which is gonna be a hash map, and then a rank, also a hash map, and self.count is what we're gonna return, which originally is gonna be n for I in range n, right? Self.parents I is gonna be equal to I, and then self.rank of I is gonna be 0 right here. So this is where we initialize everything. We will have a find function, which gonna have a self and a node, and then we just pass it right here. And then we're gonna have a union function, which is n1 and 2 union the 2 node right here. Yep. So let's try to do the find function first. So it will give a node, we're gonna find it parents, right? So what we're gonna do is we have pointer cell dot parent node. Oops, node. So we're gonna traverse. So yp is not equal of itself, so it's not equal of the parent, because we set every parent of a node in the beginning is the parent of itself. So we will escape the loop, escape the traverse whenever we find that out. So in here, basically you can do self parent. Oh, you're gonna even need to do this. So it's just this parent equal to the per self dot pair of p, and then we return p. It's just simply traverse and we return p. But there's an upgrade on this. So let's say we have a parent that look like this, right? Just like that. We are given this node, right? So we have to traverse to the root. So why don't we just, whenever we found this node, right, we just plug it in here and then make it like this, right? And if we give this node and we're trying to traverse and then go find this parent, we're just gonna remove this node and then do this, right? So this is called path compression. It will reduce the time complexity of this find function from n to log n. So yep, and then let's try to do it. So path compression is like this. So self dot parent of p current node would be equal to self dot parent of self dot parent of p. So this just make it shorter, something like that. And then this is the find function is finished from now. Let's move on to the union. So let's say we have b1, b2, the parent 1, parent 2, self dot find and 1. Then I have self dot find and 2. So let's say if the two parent is the same, right, we're not gonna do anything. We just return false. Nothing happened because they are on the same in the same component already, so you don't have to union them anymore because they have the same parent. If they are different parents, we're gonna do self dot. We're gonna check the rank of it. So if which one is smaller, it's gonna be a child node of the parent. So just stick with me right here. So let's say the p rank of the parent 1 is smaller than the rank of the parent 2. So the parent of 1 is gonna be parent 2, right? So self dot parent p1 is gonna be p2, and then the opposite. Then the other and then in the other case, when two parent is the same, we just pick a random one and plug it in. Right, so equal to p2, and then self dot rank of p2 gonna be plus equal 1. So this is where the rank is plus. If you ask, oh, why don't you upgrade the rank on this function? So let me draw it out. Let's say you have this, right? The rank is represent, what is that called? The height. So if we remove this and we plug it in here, the height is still 1. So that is why we not update the rank in here. But if there is 2 node right here and we plug it in like that, so the height is not increased. So that's why we increase the rank from there. Then next is decrement the count to return it, and then finally we return true. So that is all of our code. Let's try to run it, see if it's work. Yep, it's look like it's work. Let's see if it's right here. Yep, looks pretty good. So time complexity. So for time complexity, the find right here is cost of, but only the case that we're not using this, and the rank. If you do one of other, if you don't have a ranking system, or if you don't have this, you will receive a time complexity of this find function is log n. But in case that you have both of these on, the time complexity is gonna be even lower than that. It will be lower than that. We have it's called inversive argument function. So that math is turned into everything into of one the constant time complexity, but we're not really deep dive into that. We have to go to every single age. So let's say the age is m, right? We start to do the union both of them. So the time complexity got reduced down to O of m right here, and the space complexity is course of n, which is the node count. Yep, something like that. And hope you guys like the content. We're gonna see each other soon. All right, thank you.